Okay, more examples of rings for future reference, for future use. So far we've pretty much looked at only commutative examples. All of the examples I already wrote up last time were commutative, including the polynomial examples, as long as the coefficient ring was commutative itself. But now for some non-commutative examples, we have matrix rings. And these we've sort of already seen before in other contexts. I forget what number I was on. I could check, but too complicated. So let's just restart our numbering so this is a separate video. So we have our friend M2R, which we talked about a long time ago with our examples of groups. This is the set of 2 by 2 matrices. So A, B, C, D, where A, B, C, and D are real numbers. And it has two operations. The set has two operations. Matrix addition, which is easy. Adding two matrices, we just add the two things in the top left corner. We add the two things in the top right corner, and so on. So it's just adding 4 separate pairs. And matrix multiplication, we also know that is more complicated. But under those two operations, this is a ring. This is a non-commutative ring. Because matrix multiplication is not commutative. It does have a unity. So just to go back to our subscript notation, abstractly, I would call this 1 sub M2R. I'd never actually use that though. It's just our usual identity matrix. Lots of places will call it like I, capital I mean. So multiplying by 1, 0, 0, 1 doesn't change your matrix. So that's our unity element. I know I said that we don't really talk about units or so much when we're dealing with non-commutative rings. However, we do have the notion of multiplicative inverses, and in this context, the set of matrices that have inverses is GL2R that we're used to using it from group theory. Let me not write anything about that though. So we can construct examples using matrices. Let me adapt this example. So let's see, what can I preserve here? Erase this for the moment. So there's nothing really special about R here, that the real numbers are. I can make matrices using elements of any ring. So I'm replacing the fancy R with the ordinary R for just an arbitrary ring, capital R. But now the matrix operations are inherited from the ring R. I suppose you could come up with a very simple example. Like I could use the trivial ring that consists only of 0. The only element is 0. That would be, then make this a trivial matrix ring that consists only of the 0 matrix, and that would be commutative. But generally, whenever I make a matrix ring, the result will be a non-commutative ring, except for some very simple examples that are not worth including. So we can make these examples. Let's do a specific one with a specific alternative ring, like we do with polynomials here. So let's go back and use Z4 for our entries. M2Z4, just to illustrate what I mean by inheriting the ring operation from Z4. An individual element here would be a 2 by 2 matrix whose 4 corners are all coming from Z4. So maybe something like 3, 2, 1, 1. There's one matrix. If I want to multiply that times another matrix, say 1, 2, 0, 3, then the pattern for the matrix multiplication is the same thing that we use all the time with multiplying matrices, except now when I multiply, I'm multiplying mod 4. And when I add, I'm adding mod 4. So let's be careful here. Let's do the work first and then simplify. That may not be enough space. So if I want to know what goes here, I take this row times this column. So 3 times 1 plus 2 times 0. If I want to know what goes over here, I do this row times this column. 3 times 2 plus 2 times 3. For down here, I do 1 times 1 plus 1 times 0. And for this, I do 1 times 2 plus 1 times 3. But all these multiplications I see here are done mod 4, and the additions are also done mod 4, because that's the underlying ring operation that we're using for our entries. So we'd have 3 times 1 is 3, plus 2 is 5, but mod 4, that's 1. 3 times 2 is 6, which is the same as 2 mod 4. 2 times 3 is also 6, so we have 2 plus 2. Mod 4 is 0. 1 times 1 plus 1 times 0, that's 1 plus 0 is 1. 2 plus 3 is 5, mod 4 is 1. So my result from this computation would be this matrix. Again, my final output should have entries from this same set Z4. So everything has to be reduced mod 4. All right, so we can do this same kind of matrix construction with any ring. It just has to be some ring here so that I know how to multiply and how to add, so I can simplify all this stuff. All right. So we can produce non-commutative ring examples basically by using matrices. You have something to add, Meetsy? Come here. Got the cat showing up here. All right, another example. An example with no unity. In the way. Don't sit on the microphone. Hide behind there. There you go. All right, was no unity example. So all the examples we've had so far, we've had unity. Well, I take it back. We could depending on what ring we use for our underlying entries in a matrix, it would only have a unity if we have a unity in the underlying ring. We have to be able to put the 1 the 1R and these two entries to make an identity matrix. But we haven't even seen one example of an underlying ring that doesn't have a unity. So let's do that next. So similar to something we've done elsewhere, we can look at the integers, but then only look at even integers. So this is the even integers set. We can check that this satisfies all of our original ring requirements. It has addition. It's closed under addition and multiplication. If you add two even integers, you get an even integer. If you multiply two even integers, you get even. So it's closed under two operations. The operations are obviously associative. 0, you have a 0 element for your additive identity. You have inverses. The inverse of an even integer under addition will be even, an even negative integer. And you've got the distributive property, you've got multiplicative associativity, but you don't have 1. So there is no 1 in this set. So there's no unity element, but it is commutative. So we'll turn this into an example of multiple rings with no unity. Here's one that doesn't have a unity. It's commutative. If I made, for example, a matrix ring with even integers as its entries, now those matrices, I can only make matrices with even numbers in every place. So I can put zeros here, but I can't put the ones here that I need to make the identity matrix. Yes, I don't want to do that. All right, that was 12 minutes. One other construction I should mention that helps us make examples would be direct sums. Meets here in the way. All right, direct sums. Let's do a specific example first, and then I'll define it in general. So, for example, let's say Z4 plus Z. It's the same notation used for group direct sums. As a set, this is the set of ordered pairs where the first entry has to come from the first ring here. So this first number could be 0, 1, 2, or 3 in this case. The second coordinate has to come from the second set. So this second coordinate could be any integer. So, for example, we could have 3, 8. This is one element of this direct sum. If I want to add it to another one, say 2, 5, the way I add is in the first coordinate, my operations are done in this ring. So in this example, I would be doing addition mod 4. So I would get 3 plus 2 is 5, but mod 4, that's 1. In the second coordinate, that's just z. Those are just ordinary integers with ordinary integer addition. So 8 plus 5 is 13. So these two pairs added together give you 113. And multiplication is done the same way. If I wanted to multiply, let's just go with the same two. Multiplication in the first coordinate is done mod 4. So 3 times 2 is 6. Mod 4 is 2. In the second coordinate, I'm just doing ordinary multiplication. 8 times 5 is 40. Okay, so direct sums can be applied to rings, and you just keep both the operations, or keep both operations for each of the rings. So in general, if we've got two rings, R and S, r plus s, and we could have more than 2 actually, but r plus s as a set is the set of ordered pairs little r, little s. No, I can't slide this board anymore. It's in the way. The set of ordered pairs where the first coordinate comes from the first component, the second coordinate comes from the second component ring. I'll just say it simply, where operations are performed component-wise. So the way I multiply two of these things is to multiply the first components, and that's occurring inside of R. The way I multiply the second coordinates is with multiplication in S, and same with addition. All right, so these are just other constructions for how to come up with more examples of rings from simple examples. As we go, I'll use some of these to make examples to illustrate concepts. But let's now move on to some basic properties of rings. So one tricky thing with rings in the abstract, when we're talking about rings and properties of rings in the abstract, we're using notation like 0 and 1 and other integers, but we have to be careful how we understand what we're saying. So what I mean by that is, I'm going to prove some properties that seem obvious because they look like they're properties in like the real numbers or the integers, but we're really saying something about ring multiplication for some of these. Okay, get out of the way. All right. So our first property, good news is these things are true. So most of the things that we would hope are true, but we have to be careful and we have to prove them. So the first one is, let's see, for all of these, I don't want to keep repeating this. I may end up erasing the heading here, but we've got a ring R. I should have noted R, capital R represents some abstract ring, and when I talk about these different letters A, B, and C, they're just representing ring elements of R. All right, so the first property is, if I take A and I multiply by 0, but here for emphasis, this is not the number 0, this is the ring 0, the additive identity. When I multiply by 0, I get 0, but again, it's the ring 0. There's no integers in this picture at this point. These are all just abstract elements of whatever the ring is. Okay, and also it's the same as, doesn't matter which side I multiply by 0 on. Multiplying something by the 0 element gives me the 0 element. All right, so the proof, when I prove these things, I can only draw on the axioms that are required for a ring. So I only have those 7 properties to work with at this point. So let's prove this here, and then this equality will be similar. If I want to simplify, what is A times 0? Well, let's think about it. The only thing we know about 0 at this point is it's the additive identity. So if I add 0 to something, it doesn't change. So in particular, I can say this. 0 is the same thing as 0 plus 0. 0 plus 0 is 0 because 0 is the additive identity. So these are equal because of the property of 0. Okay, I'm going to carry on over here. I'm trying to make best use of my space here. Now I have multiplication together with addition. So I have the distributive property I can use. So I can distribute a to these two zeros. I have a times 0r plus a times 0r. Right? That's just the distributive property. Well, now let me put it all in the same place. I've got this thing is equal to this thing. So, in interest of space, let me erase. To summarize the equations I just had, I have a times 0 equals a times 0 plus a times 0. This is equal to this because that was just the transitive property of equality that we used there. All right. Now this next step we could kind of skip because with addition we're talking about group operations and we're familiar with those. But just for emphasis, whatever this is, so this represents some element. It has an additive inverse, so it has a negative. So what I can do is add the negative of this to both sides of the equation. So let's do that. Minus a times 0 plus a times 0 equals minus a times 0 plus a times 0 plus a times 0. Okay, so we know we have this negative a0. That's something that exists. I'm adding it to both sides of the equation on the left end. And since addition is commutative, I don't really have to worry about where I add it into. But the point is, when I add it to a0, these things by definition cancel. This is the inverse of this under addition, so when they cancel, I'm left with nothing. I'm left with the 0 element. And on this side, this plus this gives me 0r. And I still have one more a times 0. But 0 plus a times 0 is a times 0. And so I've got this equality. A times 0 equals 0. Similarly, for this 0 times a equals 0. I would split this 0 up into 0 plus 0 and then go through the distributive property and cancellation just in the exact same way. Okay, so multiplying by 0 is 0. All right, so that's one issue that we've now settled. The next one is the way that minus signs work. So let me carefully, this is the second property. I'm going to write three things that we hope are equal and they turn out to be equal, but we have to be careful about it. A times, by the way, I'm going to stop putting the dots because that's getting tiresome. We use standard multiplicative notation. If we juxtapose two elements, that just means multiply. So a times negative b is the same thing as negative a times b, which is the same thing as minus a times b. Okay, so the point I want to make here is there is no negative 1 at this point. There's no negative 1, so you can't really talk about a minus sign as being an object. These minuses they're just inverse notation. So let's carefully parse what's being said here with this statement. Negative b is by definition the additive inverse of b. And so I have two elements, a and the additive inverse of b, and I'm multiplying them here. In the middle, I have a times b, and then I'm taking its additive inverse. So this is saying those two processes give you the same outcome. They give you the same element at the end. And likewise at the end here, this is the additive inverse of a times b. So these are all going to be equal, but they're not equal, and they're not obviously equal. We don't have the property of we're not changing where we're multiplying negative. We're not moving a -1 around within a product. We're stating a fact about how multiplication deals with additive inverses. Okay, so let's prove this. Again, we're going to prove one of the equalities, and then the other one is similar. Which one do I want to do? So I want to prove that this is this. Well, this in the middle, that's the additive inverse of AB. So to prove it, let's look at what happens if we add A times -B with AB. Okay, I want these two things to cancel and give me 0. That would basically tell me that this has to be the additive inverse of AB. Okay, so if I have this, if I add these two things, again, I can only draw upon my original ring properties and whatever properties I've already proved. So like I just proved that multiplying by 0 is 0. But at this point, I've got an A in both terms, both of the additive parts, and it's in the same position. So by the distributive property, I can pull that A out. So this will be A times -B plus B. -B plus B is 0 by definition of minus signs. So I'll get A times 0 now. And by our previous property, A times 0 is 0. So, I don't want to erase a whole bunch of stuff, but we got this sum is equal to 0. So if I cancel the AB, I'll get, therefore, A times -B equals -AB. Right? So again, that's saying this is equal to 0, and then canceling this AB, moving to the other side, so to speak. Then we get this. So that proves this equality. This one's going to be very similar. We'll add this to AB and then factor out the B. But I'll leave that as an exercise. So again, there's no such thing, at this point, there's no such thing as -1 because we don't even know there's a 1 element. Minus signs just mean additive inverses. So next, if I have two inverses and I multiply them, the inverse parts cancel and just give you AB. So we can cancel minus signs through multiplication. This is just an application of the previous property. So from the previous property, I can take one of these minus signs and just attach it to the entire product. So we'll have this. And then by the second part of that previous property, we can take the minus from the B and move it out front. So we'd have minus AB, like this. So move this minus in front of the AB. And now we have minus. What that is doing, let's just think it through. We have AB. This minus is taking its additive inverse. This minus is taking the inverse of that. If we take an inverse twice, we're basically undoing it. Because an element and its inverse have the opposite relation as well. They're inverses of each other. It's a mutual thing. So when you do it twice, it cancels and just gives you AB. The minus cancels. Alright, so that's the short proof. I guess it's worth saying that the next one, because we're talking about these minus signs. I mentioned this at some point earlier, but we have subtraction notation. A minus B means A plus negative B. So subtraction is just a shorter way of representing addition of an inverse. So, but when we say stuff like that, we want to be careful about the relevant properties. And I want to just focus on distribution. A times B minus C is the same thing as AB minus AC. And there's a similar one for where the multiplication is on the right. All right, so let's prove this. Start on the left side and we'll turn it into the right side. So A times B minus C. Well, B minus C, by the definition of subtraction, is A plus negative B. So this is A times B plus negative C. All right, so now we've turned our subtraction into an addition, and we know that distribution works over addition. So we write AB plus A negative C. By our previous, well, by property 2, I guess it was, we can manipulate this minus sign and put it out in front of the product. So this is AB plus negative AC. But now it's adding a negative, so that's the definition of subtraction. This is AB minus AC. And so we're done. This equals this. This equals this, so that gives us this equality. And like I said, we also have distribution if the A was on the other side. B minus C times A would be BA minus CA. It's starting to rain outside, so I don't think it'll interfere with the sound, but let me do a couple more properties and then wrap up this video. Okay, so for these next two, let's talk about unities. So for the next two, let R have a unity, which we call 1 sub R. This would be property 5. Once we have a unity, so once there is a 1 element, it has an additive inverse, which we would call negative 1, so minus 1. And so what we want to say is multiplying by this negative 1 is the same thing as taking an additive inverse. So negative 1 times A is equal to negative A. And this would also be A times negative 1. Okay, so again, we'll prove one of these and the other one's going to be similar. And the way to do it is, again, similar to one of our earlier properties, we want to show something is equivalent to the inverse of an element. So the way we do that is just try adding the unknown thing in question to the element whose inverse we're trying to take. So in this case, A. So negative 1 R times A plus A. We want this to equal 0, but that's what we have to show. All right. So you have to be careful here. If in general, let me just make a note here. I'm going to erase this, but if I saw this kind of thing, B times A plus A, I'm tempted to say, well, I can factor out an A. I can pull an A out in front here and write B plus 1. That only makes sense when we have a 1 element. So if I didn't know about the unity element, I wouldn't be able to do anything with this without more information. I wouldn't be able to factor out an A, because if I factor out an A and there's no unity, there's nothing left. I don't have anything to leave behind. Okay, so what I'm implicitly needing to do then is, before I can do that distributive trick, I have to think of this as something times A. So if there's just an A by itself, the distributive property can't be applied. But if there's a unity, A is the same thing as 1 times A. And so now I have two things added together with an A in the same place. So I can pull that A out and have -1 plus 1 quantity times A. -1 plus 1, those are additive inverses of each other, so that's 0 times A. And from our first property, 0 times A is 0. So therefore, this plus this is 0, so they have to be inverses of each other. So -1A is the same thing as -A. So that's this equality. Proving this is similar, I'd just be factoring out the A on the opposite side. Okay, so again, the point of this property, the point of this property is that in the case where we do have a unity, then the negative unity element, it acts like a minus sign. Multiplying by -1 is the same thing as applying a minus sign. Okay, let me do one more. Or one more property than another statement. All right, I think this one should be pretty quick. Multiplying -1 times itself gives you 1. So -1 is its own multiplicative inverse. This should just be straightforward application of some of our previous properties. Yeah, so one way I could do it is from our second property, property 2, if I have, or actually no, property 3 does it even quicker. Property 3 says if I multiply two negatives, two things with minus signs, the minus signs cancel and just give you 1 times 1 in this case. 1 times 1 is 1 because 1 itself is the multiplicative identity element. So this times this is 1 and we're done. Okay, so that was faster than I was anticipating, which means I can say more on the next statement. All right. So I don't want to prove these. The proofs to be very similar to things we saw back in group theory. If R has a unity, it is unique. So it can only have one unity element. The proof of this is basically the same proof as saying a group can only have one identity element. If you have two different elements that act as an identity, then what happens if you multiply them times each other? Well, each one would have to give you the other because they both act as an identity element. Okay, so unities are unique when they exist. And if an element has an inverse, so A has an inverse, A inverse, it's unique. So we can call its inverse A inverse. You can't have A can't have two different inverses, and that's going to be the same proof as we had in group theory, that in a group every element has an inverse and that inverse is unique. Excuse me. All right. I guess it fits here. So let me address this next thing as well. Trying to keep my videos to be around 40 to 50 minutes at the most, so I've got a few minutes to spare here. This is just kind of a caution. If R is a ring, let's just say let R be a ring. So R is a ring. We have two concepts of multiplication. We have ring multiplication where we have A and B in the ring R, and A times B is in R. And let me double check how the book is distinguishing these. I don't always agree with the way it does this. Yeah, so I want to stop using the dot notation for ring multiplication. So in a ring, so imagine matrices, for example. If A and B are two matrices, I can multiply them with matrix multiplication and I get another matrix. That's the ring multiplication. But there's also integer multiples, which means I have a ring element A and an integer n, and it makes sense to say what is n times A, and this is where I disagree with the book. The book likes a dot in this situation. N times A means A plus A plus A n times. So this is just like in a group theory. This is like an exponent in multiplicative notation. In additive notation in a group, the exponent is really a multiple. So n times A means I'm applying my addition operation that many times to this element. So A plus A plus A n times. So you have to be a little bit careful when you're using letters to represent unknown or abstract elements of things. You have to pay attention to, and by the way, n times A will end up giving you a ring element. So if I keep adding in this ring, I stay within the ring. So both of these give me an element of R, but they're different notions of multiplication. So let me just illustrate with a matrix example. So suppose we have some matrix like this. Times another matrix. These are two elements of my matrix string. Say it's M2Z or something. But we have two elements of the matrix string. We know how to multiply. Let's do that quickly. 2, 3 times 4, 0 would be 8. 2, 3 times 1, 3 would be 2 plus 9 is 11. 1, 1 times 4, 0 would be 4 plus 0. 1, 1 times 1, 3 would be 1 plus 3 is 4. So that's one notion of multiplication. That's the ring multiplication, the bigger one. But it also makes sense to say, what is 5 times 2, 3, 1, 1? So for integer, this is tricky. So this in this example, in the matrix example, we have a notion of scalar multiplication where we can take any real number and multiply it times the matrix, which is just multiplying into each of the places. But explicitly what this means is, let me change it from 5. Let's go with 3, just so there's less writing. 3 times this matrix means I'm taking this matrix and adding it 3 times. So 2, 3, 1, 1 plus 2, 3, 1, 1 plus 2, 3, 1, 1. And then matrix addition, we're just adding the corresponding positions. So 2 plus 2 plus 2 is 6. 3 plus 3 plus 3 is 9. 1 plus 1 plus 1 is 3. And 1 plus 1 plus 1 is 3. So in the matrix example, it turns out you accomplish this just by multiplying this 3 into each place. And we get this. But this is what's going on behind the scenes in any ring example. In any ring, I can take a ring element and an integer and make sense of their product just by repeated additions. All right. Most of the time, for specific examples, it's if you're dealing with specific things, it's not hard to I mean, it's not so confusing. It's clear what the distinction is. I mean, here clearly one thing is a matrix and one isn't. But when you're dealing with abstract elements, it can be easy to confuse what exactly is going on. All right. So let me wrap up this video. I think there's a little bit more I want to say about this first section about rings. So technically we're talking about chapter 12 of the textbook. There's a little bit more I want to say there. But my plan is going forward, instead of collecting homework, since the logistics of that is not so simple anymore, what I will do is I'll still give you a list of problems from the textbook to look at, and I am encouraging you to look at those and write them up as if you were going to turn them in. But as far as a grade goes, what I will do is after I've given you some problems to look at, I will write up like a quiz type of worksheet to post on Blackboard, and even that I'm not going to collect, but what I'll do is make it participation based. I'll turn on the statistics tracking on Blackboard so I can see who downloads the worksheet, and if you download it, then you'll get credit, but you should try to do it as if it was a quiz, and then a few days later after that I will record another video of me going over the problems from the quiz, and you can watch that and then see how well you did the problems. And as usual, as always, if you have questions over them, you can ask me, and I can, if necessary, make specific question videos. Yeah, so like I said, I don't yet know how the tests will work. We've got time to figure that out, though. I promise, though, I'm going to be go out of my way to be reasonable about things in the current situation. So just do your best to follow the material, and we'll work through this together. So I'll stop the video here and pick up later.